thanks a lot, Marcelina, for the introduction, and thank you very much for inviting me to give this presentation. I'm very happy to be here today. So, as Marcelina said, I'm Greg Bedge. I'm the team lead for the photonics application engineering at Ansys in the EMEA region, and I'm happy to present you some information about photonic simulation with Ansys Lumerical. And more specifically, I want to talk about the simulation of micro LED and how we can analyze and simulate these with Ansys Lumerical. So to start with, I know that you probably had a brief introduction to the optics portfolio and numerical yesterday, I believe. But I want to go over a fairly short introduction to Lumerical and what we do and what our solvers can allow you to do. And then I will talk about the simulation workflow for micro LED, focusing on the optical side, so how to extract the emission pattern of that LED, and then also how we can extract data for further simulation in ray tracing tools like Speos and Optics Studio. And as Marcelina mentioned, after the presentation, I will be happy to answer your questions. So, Lumerical. So as you learned yesterday, Lumerical is part of the optics portfolio at Ansys. So Lumerical is part of the Ansys optics portfolio that includes Optics Studio from Zemax and Speos. The idea behind that and what it brings to you is simply that with these three sets of simulation tools, we can cover all the scales in optical simulations. So Lumerical will be used for nanoscopic simulations typically at the wavelength scale, and then thanks to the integration and the interoperability that we have between these different tools, you can model components at the wavelength scale, but then use the properties in microscopic simulations in Optics Studio and in Speos. And the LED case that I'm going to talk about is one of these typical cases where you can do these kind of very, let's say, flexible workflows. So Lumerical primarily has a set of simulation tools for photonics application, with the idea of being able to model any kind of photonic devices, whether we talk about passive components, gratings, photonic crystal, but also active components like the LEDs that I'm going to talk about, image sensors, lasers, modulators, and photodetectors for photonic integrated applications. So in order to address all these different applications, we have different types of tools and solvers. So the first category of solvers that I would want to mention would be regarding light propagation. And so we have solvers like FDTD that I'm going to talk about a bit more in the next few slides. We have the RCWA solver, the stack solver that are both for planar structures, one for periodic structures and the other one just for multi-layer stacks. And then we have tools that are dedicated for the simulations of waveguiding devices for either like fibers, but also planar waveguides in photonic integrated circuits. And we have also finite element solvers like film and DGTD. So those are really there to model the propagation of light in an arbitrary device based on the geometry, the image properties, and we basically solve the Maxwell's equation in these simulations. And then we have non-photonics solvers. So we have a charge transport solver, a heat transport solver, and a multi-quantum well solver for laser components. With the idea here, again, because with Ansys Lumerical, we're talking about photonics simulations, is that all these solvers were designed in a way to interact with the photonic simulations. So when you talk about a photodetector, you typically need an input like a light. So we can model the light propagation in the photodetector, and light will propagate here, for instance, in this waveguide and in this taper, and then it will be absorbed in the active material. In this case, it could be germanium, for instance. And the absorption of light in that material can then be used as a charge source in the charge quantum solver. And so from the combination of the light absorption and the charge transport simulation, you can extract data like the photocurrents that is generated by this detector. Without any input, you can get the dark currents and so on. So the data exchange between the photonics simulations and the multiphysics simulations is made it very easily. The other way around works as well. So here we have a case of an electro-optic modulator, or actually an electro-optic phase shifter. So here with the charge transport solver, we can model a PN junction and apply bias voltage on that junction and extract the charge distribution. And this charge distribution can be used as an refractive index perturbation for the optical simulation, and can then see how this charge distribution can affect the properties of the waveguides in terms of effective index, absorption, and so on. Again, the data exchange between the two is quite easy. And the same kind of behavior or the same kind of simulation workflows can be done with a heat transport solver for thermal simulations, where you can see the effect of temperature. Let's say if you have a heater in your system, heat will calculate the temperature map in the device, and then you can use that temperature map to see how the temperature can affect the optical properties of your device and model. So using the temperature map as index perturbation as well. And the other one, again, similar to the modulator, or to the photodetector, sorry. If you have light absorption in your device, could be, let's say, a plasmonic nano antenna, you can use this absorption as a heat source in the heat transport solver, and then see get what is the temperature elevation that is induced by the heat, by the absorption. So the key thing here is we're really talking about physics-based simulation tools, whether it's multiphysics or photonics. We are solving the physics inside the device based on the material properties, boundary conditions, and so on. On the other hand, we have a set of tools for photonic integrated circuit simulation that allow you to model complex circuits based on behavioral models. And so these models can be connected together, similar to what you would have in a SPICE simulation for electronic circuits. One thing here is that obviously you can use the component level simulation tools to generate these behavioral models. And for that, we have a tool called the CML compiler that will allow you to automate the data extraction and the generation of libraries of components. So this is mostly used by foundries, for instance. And we also have, so obviously interconnect, which is the circuit simulation tool itself. And we have a module that works on top of interconnect that is called Q interconnect for quantum computing based on photonic integrated circuits tools. So it allows you to calculate the quantum states and the probability of success and so on in a photonic circuit. So those are the different tools that we provide with Ansys Lumerical, and they all packaged in different, let's say, softwares or interfaces. So we have FDTD that includes the FDTD stack and RCWS solver, the mode environment for waveguide design that includes the eigenmode solver, the eigenmode expansion solver, and the variational FDT solver. And then we have the multiphysics environments that include that collection of solver that are based on a finite element method like charge, DGTD, film, heat, and MQW. And then on the other side, we have all the tools related to integrated circuit, photonic integrated circuit. So interconnect itself, the circuit solver, Q interconnect for quantum photonic circuit applications, and the CML compiler for the automation of the generation of model libraries based on a manufacturing process. A last comment here. So all these tools basically rely on the same set of functionalities, regarding scripting. So we have our own scripting environment that will talk about, because it's heavily used in our workflows. And we also have a Python and MATLAB API that allows you to basically drive these different workflows from these environments. This is very useful, especially when you want to run some complex workflow that can involve multiple tools, multiple solvers, and you can drive that through a scripting or through Python and MATLAB. So now let's dive in the actual application. So I want to talk about today is the micro LED simulation and the workflow that we suggest for these kind of applications. So this presentation is based on an example that we have on our website that includes different steps. So today you will see I will mostly focus on the step 3, that is the actual optical simulation of the micro LED. But this workflow can actually involve more complex steps. So typically the first part of that workflow would be to run simulations of the quantum wells that are used to emit light in that structure. So the idea is that from the layer definitions in your quantum wells, you can run a charge multi-quantum well coupled simulation to extract current voltage curves, but also the spectrum, the emission spectrum, based on the spontaneous emission that can be calculated by the MQW solver. And that can be then used later in order to get the actual emission of your LED. The second step would be to optimize the different stack. So here we have like a simple representation of this LED or micro LED. So we have different layers, and what you can really see here is that the MQW, the quantum wells, are located here. So in these kind of simulations, for the optical part, we consider the quantum well as a let's say an effective medium. So we calculate like an average refractive index for the quantum wells. But then you have multiple stacks. And what you can do is you can do a first optimization of these layers in order to get the maximum extraction efficiency. And so that can be done with the stack solver, which is an analytical solver that can analyze multi-layer stacks based on the optical properties, thicknesses, and so on. And so the stack solver can be used in 2 ways. The first way is for the codings, where we can get the reflection transmission coefficients as a function of the wavelength, thicknesses, and so on, and angle of incidence. But it can also be used for emissive structure, where one of the layers is emitting light. And so this is the case that we use here. And so the idea is that for stack, we consider that the layers are infinite in the lateral direction. But that gives a bit of an idea. So we can optimize the layer distribution in order to get the best emission and extraction. But since we're talking about micro LED, here the LED has a finite size that is of a few micron. And so we have to take into account that finite size in the lateral direction. And so that's why we have to switch, once we kind of have a first idea of the stack distribution, we have to switch to a full 3D FDT simulation in order to analyze that micro LED, and then calculate the emission pattern of that LED, the extraction efficiency, and so on. And this is the flow that I will talk about mostly. And once you're done with the optical simulation of your micro LED, then you can run some other simulations in order to extract data. So here, for instance, we can export the emission pattern either as a spectral intensity for speos, but you can also export the emission as a ray set that can be used in Zemax Optics Studio. Okay, so again, here we're going to focus on calculating the emission pattern of the LED, considering that the LED will emit light that is incoherent and unpolarized. And so for that, we will use the finite difference time domain solver from Ansys Lumerical. So what is FDTD? So FDTD is simply a fully vectorial 2D, 3D maxwell solver. So what we do is we calculate how light can propagate in the geometry, in the volume, by simply solving the Maxwell's equation in time domain. So the algorithm is very well known. I think the first description of this algorithm dates from the 1960s. And it's been widely used in various applications from photonic simulations, but not only photonic simulations. One of the big advantages of the FDT method is simply that it doesn't rely on any kind of approximation. The only approximation we can do here is related to the meshing, so the discretization in space and in time. And because there's no assumption or approximation, the FDT method can be used in a wide range of applications, going from integrated optics, image sensors, solar cells optimization, LEDs and organic LEDs, nanoparticle scattering, plasmonic applications, and so on. So one question that can come to your mind is, what is the common point between all these applications? And so, or put in a different way, what is when should we use a simulation method like the FDTD compared to ray tracing, for instance? And the simple answer to that is just related to the feature size of your device. If the feature size of your components are about the same scale, the same size, of the same order of magnitude as the wavelength, that's where you should consider full wave simulations like the FDT method provides. Just to illustrate this, we can have a look at this very simple simulation. So it's a grading, like a sawtooth kind of grading with an angle of 45 degrees. And we can simply apply Snell's law. With this refractive index, we have a 45-degree angle of incidence. We know that the critical angle is 41.8 degrees. And it means that at normal incidence here, so at 55-degree incidence compared to the interface here, we should expect 100% reflection because we above the critical angle. So to illustrate that, we've run two simulations. We created this grading structure, periodic structure, illuminating it with a plane wave. So the structure has a period of 20 micron, and we run a first simulation using a wavelength of 400 nanometer. So here the wavelength is much smaller than the period of the grading, and you see that when the light is propagating here and reaches the grading, we have more or less what we expect, which is total reflection of light from that structure. But then if we run the same simulation, but with a 4 micron wavelength, so it's much closer to the size of this grading, we see a completely different behavior. And instead of being fully reflected, part of the light is transmitted and part of the light is reflected. So this is just an illustration of what I want to say, is that a simulation method like FDTD, where we solve the Maxwell's equation, is really necessary when the feature size of your device on the same scale as the wavelength of interest. So obviously, whether you're interested in visible light or infrared light or UV light, that will completely change basically what kind of feature size we're talking about. So another thing is, as mentioned, FDTD is a time domain method. So we calculate how the fields are propagating as a function of time. But in most cases, what is of interest is not necessarily the fields as a function of time, but more the fields as a function of the wavelength or the frequency. And here it's fairly easy. The only thing we need to do is to run a Fourier transform. During the simulation, we use a discrete Fourier transform in FDT in order to get the frequency domain fields as a function of the time domain fields. And further than that, we also do a normalization. So we normalize the frequency domain fields obtained by that Fourier transform to the source spectrum. So the idea here is that we can get the impulse response of the system that is completely independent of the spectrum of the source. why we do that is, ideally, if you inject light in a source, I mean, the easiest way you could think of is that you inject light with a constant spectrum. So you have the same energy, the same intensity at every wavelength or every frequency. But the problem is, because we're in the time domain, having a constant spectrum would mean that the time domain, the pulse, the time domain description of the light that we inject in a simulation would be a delta function. And injecting delta function is simply numerically not practical. So instead of trying to inject a delta function as function of time, what we do is we inject a short pulse that is basically defined based on the bandwidth of the source that you need. So in our workflow, the one thing we are interested in is to get the incoherent and unpolarized emission of that LED. The difficulty here is that by essence, FDTD is a coherent method. So it means that the light you inject is coherent. So if you have multiple sources, they will interact between each other, and you have some interference pattern. So the question then is, how can you obtain incoherent results from a simulation method that is inherently coherent? So a first way to look at it, or to first way we could use to do that, would be to use the ergodic principle. So here the idea is that we generate a dipole cloud. So each source here that is represented by this little circle and the arrow will have a random orientation and a random phase. And then what we do is, for each, we run multiple simulations, each of these simulations with a different distribution of sources, and combine these distributions. The problem is that first we need a large number of sources, but also we need a large number of simulations, because we have to repeat that to get some statistical, to reduce the statistical error associated with this method. So a big mistake that some people often do when they try to apply that kind of thing, that kind of method, is to assume that only one simulation is enough, since we have maybe hundreds or 50 to hundreds, whatever, random sources in a simulation. That's not the case, and typically you often need something like 50 to hundreds of simulations as a minimum in order to reduce that statistical noise. So in terms of efficiency, it's definitely not the best way to do that. And the key thing here is that we can actually obtain the same results from coherent simulation without any statistical error, but also with a much smaller number of simulations to obtain these results. So if we look at, let's say, dipole emitters, dipole sources, and what happens if you want to get some the fields emitted by incoherent dipole emitters. If you put two dipoles in the same simulation, as we see here in this animation, you see that the fields interact, and we have this interference pattern that results from those two sources. So how can we get incoherent results out of that? But here what we can do is we can simply run two simulations, one with each of the sources. And obviously, since there's there's only a single source for each, we don't see that interference pattern. But what we can do then, we can combine the results of those two simulations. So if we add the fields currently, so basically we add the fields as vectors, we see that we get back to the coherent behavior. We have this fringe pattern resulting from the interferences. But if we had if we add incoherently the fields, so basically what we do is we add the field intensities, absolute square value of the two fields. Then we have the incurrent behavior of that dipole, of those two dipole sources. And this is how we can get the incurrent results out of a current method as FDTD. And this is what we're going to apply in our workflow today. In a similar way, we can extract unpolarized results. When you inject light in FDTD, the light will have a very well-defined polarization in the sense that we are defining the angle or in what direction the fields are polarized. And this is represented in the simulation by two arrows. Just realized I need to update the screen capture. So the blue arrow that you see here represents the orientation of the electric field. But when you will see in a tool that's we also have a green arrow for sources like here a Gaussian beam that represent the orientation of the magnetic field. So how can we get unpolarized results from polarized simulations? Similarly, as we did for the incurrent results, we just need two simulations with orthogonal polarizations. Typically, we use 0 degree and 90 degree. And then we do the average, the incurrent average of these two simulation to get the unpolarized results. Only with two simulations for this kind of source with a Gaussian beam. But if we're talking about dipole illumination, as we will do in the micro LED workflow, then we need the three simulations. Actually, we need three orientations along the X, Y, and Z axis, and we combine incurrently these results by averaging the absolute square value of the fields. So that's how we get incurrent and unpolarized result out of the FDT method. And this is what we're going to simply apply for the macro LED simulation. So in this macro LED simulation, as I mentioned, we consider that the light is emitted from the quantum wells, and we will use dipole sources in this quantum well to calculate the how light is extracted, is generated by this LED. Obviously, light is not emitted at a single point. So in order to get the actual emission of the LED, we need to sweep over the position of the LED in order to cover the area where the light is emitted from. Here we have an easy case because the LED has a cylindrical symmetry, and so we will use that to simplify the workflow. Because of this cylindrical shape, we can only limit the workflow to sweeping the position of the dipole along the radius of the micro LED, and we don't need to change anything else because from that position we can interpolate or deduce the emission from any angle along this emission, this LED. Obviously, if your micro LED didn't have that cylindrical or revolution symmetry, we would have to run a sweep over the XY position of the dipoles, and that would increase the number of simulations, but the actual workflow would be more or less the same. And then again, as we just discussed, once we run the simulations over position and polarization to extract the incurrent unpolarized emission of that LED, we can sum incurrently to get these unpolarized incurrent results, and we can extract information like what is the fraction of power that is emitted by this LED, and also what is the angular distribution emitted by that LED, so the field intensity distribution emitted by that LED. And to do so, we are using far field projection. So far field projection is a very interesting method that allows you to, from an FDT simulation or any kind of Maxwell's equation simulation tool, we record the fields at a certain location. Here, for instance, the plane symbolized by these dotted lines. And from that simulation in time domain, we can extract, again, as I mentioned, the Fourier transform to get the frequency domain fields, but we can run a far-field projection. So the far-field projection simply assumes that the propagation of light from that plane is in a homogeneous medium. So there's nothing in that will affect the propagation of light. And then we can calculate the fields at any position above that line. For this specific case, we also use another thing, is the fact that if we know the fields on the six sides of a box, we can know the fields at any position outside of that that box. And this is what we use here in order to calculate the angular distribution of the LED. By simply showing, I would say that, by calculating the far projection, and we get basically, we're projecting the fields over a 1 meter radius hemisphere. That gives us basically the angular distribution as you see here. Here we have the result for like one of the polarization, position, and wavelength points. And once you have done all of this far-field projection, so we have the angular distribution, we have the fraction of power that is emitted. We can run some post-processing in order to get the light extraction efficiency. So here, for instance, we get the fraction of power through what we call monitors that record how the field propagates, normalized to typically what is how you say that, normalized to what would be emitted by a dipole in a homogeneous medium, and then you can also get, so you will see in the simulation that the simulation is set with the LED located in a sapphire environment, in sapphire material, and we can also compensate with what to do some processing in order to get what is the actual emission in air, so taking into account the sapphire air material interface. And we can also apply the emission spectrum that can be calculated from the quantum well simulation, where we get the spontaneous emission spectrum for light with a polarization parallel to the quantum wells or orthogonal to quantum wells. And we can simply apply that spectrum to the emission that we calculated, and you get the actual emission for the actual emitted power for that LED. And we can also calculate the efficiency, how much of that power is within a certain emission cone. So here, for instance, you can see that the emission of that dipole is in the is a red LED. So we're around like 630 nanometer wavelength. Lastly, once you've done that, so those are the main, let's say the main data you want to extract from your simulation. Then you can also export data for ray tracing software. So here, for instance, we have an example where we calculated the emission from an organic LED with a nanostructure, and we used that. We exported that as a ray set for Zemax Optixio, and then we could use that ray set as a source, as a bunch of rays emitted from this line of LEDs. Or you can also extract, which is the case in our example, the spectral intensity map that can be used in SPEO. So here you see the angular distribution of intensity at different at a specific wavelength. That can be used as a light source in SPEOs, and you can then analyze. Here, for instance, we use that in a screen, like a cell phone, a mobile phone simulation to see first what is the actual emission, or how the screen looks like, but also how the eventual coatings, anti-reflective coating, and so on, and how the ambient lighting can affect the visibility and so on. So those are the different things you can do, and it's probably a lot of more things. So now that I've talked about the actual workflow, let's switch to the actual simulation file, which should be here. So here's basically the Lumerical FDT environment, where you see the geometry. Basically what I described earlier, we have the quantum well layer here, and we have the different stacks. We have a substrate, we have different materials, aluminum, indium phosphide, and so on. So those define the different things. Just to briefly describe the user interface of FDTD, we can set the simulation in different ways. So by default, we have materials that are provided from the literature. So we typically have different sources. We have the Pelican book, the CRC, and Johnson and Christie's. So each of these materials are considered as dispersive materials, where the refractive index, real and imaginary parts, are described as a function of the wavelength. Obviously, you're not limited to these materials. You can import or add whatever material provider that you know their properties. We have a lot of different material models that can be used. The main one, I would say, would be the sampled 3D data, which is the material model that is used in these materials that provides like the dispersive information as function of the wavelength or the frequency. And so here you see we have a bunch of materials that are defined that we imported from the example that we used as a reference. We have an active material that is considered as a dielectric, the MQW material, and so on. So once you have your material defined, then you can generate or create a structure. So there's multiple ways to define your geometry. We have a set of primitive objects that can be easily added to your simulation. Just click on the button. Could be cylinders, could be rings, rectangles, or more like complex elements. You have the possibility to import data. So in terms of import, it could be the layout, so a GDS file. So the interesting things, the interesting thing with the importing GDS is that you can use this object here, that is the layer builder. Typically, we use that more in applications like photonic integrated circuits, where it's widely used. So basically, you have the layout mask that define all the different layers, and we can define what is called the process file. The process file will include all the information about the layer definitions, what materials for each layer, what are the thicknesses, and so by combining a GDS file and a process file with a layer builder, you simply automate the creation of a stack like this. Here we didn't use that. What we used is what we called a structure group. It's a parameterized description of the geometry we have here. So if I edit that macro LED structure group, you will see that I have a bunch of parameters, properties that were defined. The first property is the radius of the macro LED. So here we have a radius of 2 micron. And then we have these 9 layers where we define what material is used for each of these layers. And then we have what is the thickness of all these layers, going from 100 nanometer to 1.2 micron for the first layer. So when you use these kind of elements, these kind of objects, so you define the properties of interest for your geometry, and then in the script you have the script that will use those elements in the simulation. So here. The geometry is very simple. We, since it's a bunch of disks that are stacked together, so we define different arrays with the properties for the materials. the thicknesses, and then we run a sweep and add a circle or a cylinder for each of these elements, changing the names, material properties. The radius is always the same. And then the X1 position, it's centered to the simulation region, and then the position in a z-axis. So the script here is very simple, but it allows you to create that stack in a very easy way. And the good thing is, now that you created that element, you can simply change whatever value, let's say, of whichever layer you want to change, and it will adapt automatically thanks to the script that is here. Then we have a source that you can't see here because it's hidden inside the structure, but that's the dipole source that we use for the illumination. We have this orange box that is the FDT region. So what the FDT region defines is the simulation volume. Where do we calculate, how do we calculate light? So also because of the way, or because of the structure, so here we have, as I said, it's a cylindrical structure, so we have symmetries. So to reduce the simulation time, what we do here is that we use the symmetries to reduce the simulation volume by a factor of 4. So in practice, what we do is we simply model a quarter of the simulation volume, this top right corner here. And the when we get the results out of the simulation, these results from 1/4 of the simulation are automatically unfolded based on the symmetries that we used here. So that's very efficient to reduce the simulation volume and obviously the simulation time. Then we have what we call monitors, or just before getting back to the simulation region. The simulation region is basically where the main simulation parameters are defined. So if it's 2D or 3D simulation time, why we have that is, again, FDTD is a time domain simulation method. It means that we calculate light as a function of time. Light is propagating, and we have to basically set an endpoint. So how long do we can we let the fields propagate in a simulation volume? So here, for instance, we set the simulation time to 500 femtoseconds. The default value is 1,000 femtoseconds, and it can depend. I mean, sometimes you need less, sometimes you need more, depending on the size and the kind of devices. So for resonance structure, the simulation time can often be larger. In other cases, we can reduce just the simulation time. One key thing here is, as I mentioned earlier, in order to get the fields in the frequency domain from the simulation, we use a Fourier transform. And that Fourier transform, to be valid, we need the fields to have decayed enough by the end of the simulation. And so we use a feature that is called the auto shut-off feature that monitors the amount of energy that is left in the simulation volume. And when that amount of energy has decayed enough, we simply stop the simulation. And that threshold is defined in the advanced option. So what it means is that even though we set here a simulation time of 1,000 femtoseconds, doesn't necessarily mean that the simulation will run for that amount of time. It can be stopped before if we consider that the fields have decayed enough, which can also save a lot of time. So the other parameters that we have here would be the simulation temperature. So this has an effect on your simulation only if your materials are defined as index perturbations. It means that you defined material that are temperature dependent. So by default, it's not the case, so this won't have much impact on your simulation. What is more important is the background material. So we basically define what is the refractive index or what is the material properties used anywhere in a simulation volume where no object is present. By default, we use vacuum, so the refractive index would be 1. But here, as I mentioned, we have simply set the structure to be in a sapphire layer, and so we have a refractive index of 1.77. It could also be one of the materials from the database, as you can see here. Then you can define the geometry, so basically the size of your simulation volume, the mesh information that will obviously impact the accuracy of the simulation. So the mesh is defined with this slider called the mesh accuracy, and that simply sets a target for the number of mesh cells per wavelength. The slider goes from 1 to 8, the default value being 2. Here we set it to 1 simply to get faster simulations. And so that corresponds to 6 mesh cells per wavelength in a material. And then a mesh accuracy of 2 is 10 mesh cells per wavelength, and so on. It's important to remember here that we talk about the wavelength in the mesh cells per wavelength in the material. So it means that we take into account the material properties. So if you have a high refractive index material, the wavelength will be smaller, and it means that the mesh will be smaller, and that impacts obviously the amount of memory that is required for the simulation and the simulation time, how long it's going to take to run. Other factors or other parameters are not necessary. There's parameters related to the time step that is automatically calculated based on the mesh size. We have mesh refinement that are just additional additional processing around the material interfaces to simply increase the accuracy of the calculation, knowing that FDT is a finite difference simulation method. So we use an orthogonal mesh to discretize the structure. And obviously, when you have to discretize a non-planar structure with a rectangular mesh, you have some staircasing effect. And so the mesh refinement, the conformal mesh technology that we developed allows you to reduce these staircasing effect and get a better accuracy for the same mesh size. Another important parameter would be the boundary conditions. So as I mentioned, here we use symmetries to reduce the simulation volume. So we use anti-symmetric boundary conditions and symmetric boundary conditions. Why we use one or the other depend on the field orientation, because the way the symmetry acts is different. Or let's say what components of the fields can be non-zero at the plane of symmetry will impact which symmetry to use. And we use we use that in x-mean, which is that plane, and the y-mean, which is that plane. And in the z direction or the other, we use PML boundary conditions, which are simply absorbing boundary conditions that allow you to simulate like an infinite propagation within a finite size simulation volume. Yeah, and that's basically, I won't go too much to details in the advanced option. The only thing is the thing that I mentioned earlier, which is the auto shut-off. And so here we have the threshold that is set by default. It's 10 at the power of -5. And so once the auto shut-off value goes below that value, simply we stop the simulation, because we consider that the fields have decayed enough. So that's for the simulation settings. And then we have the monitors. So the monitors are basically the objects that we use to record the information in the simulation volume. So here you see a bunch of different monitors. We have okay. So they're symbolized by either yellow lines or yellow rectangles, as here. So here you have monitors recording the fields in a y normal plane, x normal plane, and z normal plane. And we also have time monitors. So time monitors will just record the fields as a function of time. And these ones are point monitors. So they just record at the single location. And most important for our case is the far field analysis group. So this is similar to the structure group that I mentioned earlier for the macro LED geometry. We have these analysis group that allow to group multiple monitors, like here, and to do some post-processing in terms of using the data recorded by these monitors to calculate more information. And so here we have a box that is surrounding the LED, and this is what we will use in order to calculate the far field projection and to get the emission of light out of that LED. And in a similar way as we had in the structural groups that defines the macro LED, we also have some parameters that are set. So here the parameters simply define the geometry, the size. So we have X span of 4.5 micron, Y span of 4.5 micron as well, and the Z span of 5 micron. A key thing here is for this LED, the emission is going upward. So we shouldn't have any emission in the downward direction. So here we have this additional parameter that simply tells us whether or not we want to include the bottom monitor in this analysis group. And if you look at the element here, the bottom monitor that you see here is actually disabled, and you won't see it. And this is done in the analysis group. So we have the properties, and then in the scripts we have the scripts that simply sets the dimensions of the monitors based on the 3 values you have here, and then it will enable or disable the bottom monitor based on the value of that variable. So that's for the setup, which means basically how this box of monitor is built. And then we have the analysis group. So the analysis group defines the analysis tab, sorry. The first bit is the parameters that are used for the analysis. So here we define the resolution in theta and phi, whether we do the far field projection for all wavelength or for a single wavelength. So we could limit the far projection to a target wavelength. And we can also downsample the near field for the far field projection to kind of speed up the simulation. So those are the parameters of the analysis. And then here we have results that are calculated by this analysis. So we get the pulsar factor, the angular distribution of the Poynting vector, the transmission, which is the fraction of power flowing through the monitors, and the far field projection. And these results are calculated from that script. And so you have all all the details of the script. I won't go over all of this because that would take potentially a lot of time. But basically, yeah, you can do anything almost that you want to do using the data we extract from these monitors, and that's basically what you get here. We get a transmission, and we can also figure out whether there's if symmetries are used or not. Everything is basically dealt by that script, and then once we extracted the data, we can package those data using data sets and generates the information. Basically, generates the results that we defined in this tab. So here we define the transmission, and then we do the far field projection, and so on and so on and so on. So that's the simulation setting, and then to get to the workflow. So as I described in the slides. Here, what we need to do is we need to sweep over the dipole source position and the orientation of the dipole. And this is not done here directly, although there's one thing I didn't show is that the model object here is also a group, and that's where we set 2 parameters. The parameters that we use in that sweep, which are the position of the dipole. So here, for instance, the dipole is at the center of the simulation or the LED, and the axis, or the basically defining the polarization, the orientation of the dipole. And here we have the script that sets the position of the source and then the orientation of the source, and based on the orientation, we will adapt which symmetry boundary condition we use between antisymmetric and symmetric. Why we do that is because now in order to sweep over these values, we will use the parameter sweep and optimization tool that is provided with Lumerical tools. That is a functionality that is on all our tools, and we have defined a nested sweep. So the first sweep will change the polarization. So if I edit its properties, I have 3 values, and we use that property that I just showed, axis from model here, and we assign the 3 values, 1, 2, or 3, corresponding to X, Y, and Z polarization. And then here we define what are the results we want to get from that parameter sweep. And so we name them P, far field, T for transmission, plus a factor, and we select what results or where do we take these results from. And you see that all these results are taken from the far field analysis group that I just showed a few minutes ago. And so those are the results that we're extracting from each of the simulations. Again, as I said, it's a nested sweep. So we sweep over the polarization and we sweep over the position. So here, the dipole position goes from the center to 1.9 micron, which is near the edges. So if you remember, our LED has a radius of 2 microns. So we're basically 100 nanometer from the edges of that LED, and we use 11 points. So we have 3 orientations, 11 points, which means that the actual simulation is running 30, or the actual sweep is running 33 simulations. So let's see if that works. So then if yeah, of course not. Yeah, I'm going to change the view to the where is it? So the classic view. The reason why I want to do that is so you can see. So you remember in the previous view, there's some information that were not visible, like the point monitors and the source. So now you can see the dipole. So here it's oriented along the x-axis, so with the axis set to 1. And if I run the animate button, oh, it's actually not changing anything. Interesting. I have to check why. Anyway, normally you should have seen the position and unless I'm on am I on? No, I haven't run that. Okay, interesting. Anyway, I need to figure that out. Normally you should have seen the polarization changing and the position of the dipole changing here. So yeah, I should have checked that. But yeah, so basically that's what we do. So here I won't run those 33 simulations because that takes a bit of time. But actually, what also takes a bit of time is the processing, because we have to run the far field projection for that, and so the far field projection, yeah, can take a bit of time. So for that, yeah, I run the simulation before. Things that can help to speed up the simulation is parallel computing or high performance computing. So the way we run the simulation, so if I just wanted to run that simulation, I could just click the run button, have different options. I can run on CPU, I can run on GPU. My laptop has a small GPU, so I could run that on my laptop on GPU. We also have now that is available from normally today with a 25 1.3 release. FDT is capable of running simulation on Ansys Burst. So Ansys Burst is a new product from Ansys that allows you to run your simulations on the cloud from the user interface. So basically, it will, if I should be connected, let's see, I won't run the simulation again, but it will open this interface. You have your accounts, the credits you have, how many credits you need to run that, not to run the simulation, but how many credits per hour that type of instance would use. So either you can just leave the tool to choose the instance by automatically based on the simulation size, or you can manually choose which type of instance you want to use. So basically using which type of processor. So here, for instance, we're using 31 cores, or we can use 63 cores. You see that the memory available is different. And so once you select your settings, you click submit, the FDT will upload the simulation files to the cloud burst environment, queue the job in the cloud. Once if the resources are available, the simulation will run. And once the simulation is done, we get the results back. The interface will download the simulation automatically for you. So that's for single simulation, but you can also do the same for a parameter sweep, where you can use the burst button here, the cloud button, that will run that for you. So that's a nice way. Or you can also run, let's say, manually set different resources for this sweep. So here, for instance, as I mentioned, I have a GPU. It's a small GPU, so I could run my simulation on GPU. By default, I'm using the CPU. I don't have many cores, so it's not like the most powerful. But I can also submit jobs from this interface on our HPC. So this is our internal HPC. So it's not on the cloud, it's an on-premise cluster, where I can specify using Slurm how many, what partition I want to use, and I have an environment that will define where to upload the files and so on. If you're on a cluster environment like that, we also have a Python module that is called lumslurm, that allows you to submit jobs to a cluster environment using the Slurm job scheduler. I cannot show you, unfortunately, like that, but it's a very cool Python module. The reason why it's very interesting is because it allows you to submit the simulations. So we have that run solve simulation, where you specify the simulation file, the partition, how many nodes per calculation you want to use, how many processors per node, how many threads per process. Is this a GPU type of partition that you have? So how many GPUs do you want to use? And so this module will submit the job, or queue the job, the simulation in a job scheduler, and then with those resources that you've done. That's not the most interesting bit. The interesting bit is that you can do the same with a parameter sweep, which is the case here. So when you have those type of complex simulation workflows that involve here 33 simulations, we can use a Python method like run sweep. Again, specify the simulation file, the parameter sweep name, and then we have to define what partition is used for the FDT simulations. That's the solve partition, with a number of nodes per simulation, number of threads, number of processors. And then you can also specify, if difference, which partition to use for the processing. And the processing, which here will here be the how you call that, the far-field projection, for instance. And what that method does, which is super interesting, is here you are actually an example of how to submit a job for exactly that case that we're looking into. The interesting bit here is that, so this command, this function method, will first generate all the files so the 33 simulations for that parameter sweep, and then it will submit these 33 simulations as individual jobs for the FDT simulation. So those will be submitted in that partition, for instance, but also jobs for the processing bit. So at the end, you end up with 67 jobs that are interdependent, meaning that the far field projection, the script job, will only be started when the corresponding simulation is done. And so why there is 67 jobs is because you have 33 jobs to run the simulations, the 33 simulations. You have 33 jobs for the processing, the far field projections. And then we have a last job that is to load all the simulations back into the main file. And when that is done, you have all your simulation files, all your results stored. Oh, good. Okay, let me just reload the same file. Up, open. Okay, we have all the results in the parameter sweep that is defined here, and this is symbolized here by this little red icon. And so if I select that, I can right-click on the sweep, or I can look at the result view here, and I can visualize the different results that I've had calculated. So here, for instance, I have the far field projection as a function of the wavelength. So I can here slide over the wavelength, and you see that the effect, the field distribution is highly wavelength dependent. Here I also have the results for the different polarization. So you note here that we didn't average the different polarization. We could have done that, but we chose not to. The reason being is that it allows us to have access to the individual results, and that's widen the range of post-processing that we can actually do for this workflow. So if you remember what I was saying in the when I was talking about the very first description of the workflow, the first step we can use is to use the MQW solver to calculate the spontaneous emission spectrum of that LED. But this spectrum will depend on the polarization. So we can have a different spectrum for the TE polarization, which is parallel to the quantum wells, or different spectrum for the TM polarization along the Y, the orthogonal direction. And since we have these different spectrums, and since we have the results stored for the different polarization, we can apply those spectrum separately on the different polarization. So that's why we didn't do directly the averaging of that far field projection. So here again we have the position, the orientation, and the last parameter we have here is the position of the dipole. And so that gives you the possibility to simply look at how the data, the emission looks like. But to do the actual processing, we are using a script. So if I go back to my user interface, I have a script file editor. I already loaded the file. So the example is provided with quite a lot of different scripts that are doing different things. First, we do an analysis with a single dipole position. So we're just looking at the emission when the dipole is at the center. But here we're looking at the emission of this LED, taking into account the full range of position and polarization that we set up. So the script basically first checks whether we have run the sweep or not. So if this command doesn't return 1, we run the sweep and we save the results. But here we already run the sweep, so we don't have to do that. And then we just get the results. So we extract the power as a function of the angle of emission. We do some averaging on the dipole positions, and you can also do that for the orientations, and so on. Here we do analysis, or it's commented in that, but you have the possibility to compare the results of this analysis depending on the number of dipole positions that we use for the processing. So as I said, we use the simulations are run with 11 dipole positions, but you can do the processing every second position or every fifth position and compare the results. The idea here is to kind of try and figure out what is the optimum number of dipole position that is required to get an accurate result. Why we would want to do that? Simply because we don't want to run too many simulations. So if we can reduce the number of simulations, that kind of reduces the time required to get those results. So here we consider that all the dipole have the same way, in the sense that the emission of the dipole is the same whether you are at the center of the LED or towards the edge. That's not necessarily the case, but you can adapt that by changing the weight function here. And that's where you apply the weight. Here you define the weight function, and here you apply that way. And then we use a Gaussian spectrum here in order to get the power versus emission angle, and so we simply apply that Gaussian spectrum. Here, instead of using Gaussian spectrum, we could use the results from the MQW simulation, for instance, and we do the integration over the what you call that, what is it here, over the wavelength? No, the wavelength. It's normalized to the integration of the wavelength. Here, basically, we know that the emission, or we define that spectrum to be centered around 625 nanometers, and so we do this power density around that wavelength, and so that's what we do here. So yeah, we have a lot of different things, and if I click run, it shouldn't take too long because all the results are already done, and we get automatically the different plots. So here we have the dipole spectrum that I mentioned, and the how you call that, the dipole spectrum, the angular distribution, either at a single wavelength, so 625 nanometers, or integrated over the bandwidth of the simulation, take into account that spectrum. And then we have the normalized power emitted to here. So again, here we consider that the structure is in a sapphire environment, in sapphire layer, and we compensate using Fresnel laws to get the fraction of emitted power in air compared to taking into account the sapphire air interface. So that's one a first script you can run. As I said, there's plenty of different scripts that are provided. Another one that is interesting is the spectral intensity file. So this one requires a different file. So I'm just going to open the other file, which is the Lumerical Speos export. Why do we have two files? Is simply because we don't do the far field calculation the same way. Let me just check that. Far field power. Yeah, so in order to do the export for Speos, we need to calculate the far-field projection in a conoscopic coordinate system. So this analysis is slightly different. It's here. We see similar parameters, whether we want to project all the wavelength or a single wavelength, how many points for the resolution, do we use symmetries in a simulation, and so on. And yeah, just look, the script does similar to what we did earlier, but simply in a different coordinate system. And we can then run that script, and that script will generate a data file that I need to find. Here it is. Macro LED. Up, here we go. So that script is generating this speos export radiometric file that we can edit. Just making sure I don't have any thing. Yeah, okay, yeah, it should work. So here you see basically it's a text file. It's a very simple file, but it could be fairly large. So I won't run the script because it takes a few minutes to run. But what I can do is I can open speos photometric lab, and I can import that file as soon as I can find my window. I'm just going to close this. Okay, here it is. Here I have my window, so I can import the text file that I just showed you. It's a bit of a big file. So by default, it shows all the wavelength and so on, but you can basically look at the different wavelength and see the angular distribution. And so that shows in true color, but I can also look at just like the intensity. Oops, no, wrong one. That's the one I wanted to check. And I can change. You can see the angular distribution for the different wavelength, and you see that obviously as soon as I get too far away from the emission, the peak emission wavelength of 620 something nanometer, I get barely anything. So if I go back to here, which is more or less where I have the maximum intensity, and this gives us basically the angular distribution, and that is what is then that can be used in speos for including this LED system in a more like macroscopic simulation. Okay, so yep, that's all I had for today. So thanks a lot for your attention, and thanks a lot for attending this webinar. If you have any questions, feel free. Be happy to answer them. Thanks a lot, everyone. Thanks, Marcelina, and have a great day. Bye-bye.